Nuclear fusion in stars, how the sun and stars get their energy. Here on the Earth, 150 million kilometers from the sun, a surface of 1 meter square in area exposed to the vertical rays of the sun receives energy at a rate of about 1.4 kilowatt. Adding up all the energy radiated by the sun per second gives an enormous total of 4 into 10 to the power 26 watt, and the sun has been emitting ray energy at this rate for billions of years. Where does this all energy comes from? The basic energy producing process in the sun is the fusion of hydrogen nuclei into the helium nuclei. This can take place in two different reaction sequences, the most common of which, the proton-proton cycle, is shown in 12.26. This is 12.26 proton-proton cycle. The total energy, evolved energy, is 2.47 mega electron volt per helium nucleus formed. Since 2.47 mega electron volt is 4 into 10 to the power minus 12 joules, sun's power output is of 4 into 10 to the power 26 watt, means the sequence of reactions must occur 10 to the power 38 times per second. Right? The sun consists 70% hydrogen, 28% helium, and 2% of other elements. So plenty of hydrogen remains for billions of years of further energy production at its current rate. Eventually the hydrogen in the sun's core will be exhausted, and then as the other reactions described below take over, the sun will swell to become a red giant star and later subside into white dwarf. Self-sustaining fusion reactions can occur only under the conditions of extreme temperature and density. The high temperature ensures that some nuclei, those in the high velocity tail of the Maxwell-Boltzmann distribution, have the energy needed to come close enough together to interact, which they do by tunneling through the electric potential barrier between them. At the 10 to the power 7 Kelvin temperature typical of Sun's interior, the average proton kinetic energy is only about 1 kilo electron volt, whereas the barrier is about 1 mega electron volt, a thousand times higher. The high density ensures that such collisions are frequent. Further condition for the proton-proton and all the other multi-step cycles is a large reacting mass such as that of Sun, since much of the time may elapse between the initial fusion of a particular proton and its eventual incorporation in an alpha particle. So the proton-proton cycle, this is the chief nuclear reaction sequence that takes place in the stars like Sun and the cooler stars. Energy is given off at each step. The net result is the combination of four hydrogen nuclei to form a helium nucleus and two positrons. The neutrinos also produced are not shown. Hence, Hans A. Bethe was born in Strasbourg, then part of the Germany, but today of France. He studied physics in the Frankfurt and Munich and taught at various German universities until 1933, when Hitler came to power. After 2 years in England, he came to the United States, where he was professor of physics at the Cornell. From 1937 to 75, he has remained active in research and in public affairs, even though formally retired. Notable among Bethe's many and varied contributions to physics in his 1938 account of the sequences of nuclear reactions that power the sun and stars, for which he received the Nobel Prize. During World War II, he directed the theoretical physics division of laboratory at Los Alamos, New Mexico, where the atomic bomb was developed. A strong believer in nuclear energy, It is more necessary now than ever before because of global warming, but he also had been an effective advocate of nuclear disarmament. The proton-proton cycle dominates in the Sun and other stars with less than 1.5 times the Sun's mass. In more massive stars whose interiors are hotter, the carbon-carbon cycle is the main energy source. The cycle proceeds as in figure 12.27. The net result is again the formation of an alpha particle and two positrons from four protons with the evolution of 24.7 mega electron volt. The initial carbon 12 acts as a catalyst for the process since it reappears at its end. The dependence of two cycles on temperature is shown in figure 12.28. Formation of heavier elements fusion reactions that produce helium are not the only ones that occur in the Sun and other stars. When all the hydrogen in a star's core has become helium, gravitational contraction compresses the core and raises the temperature to 10 to the power 8 K needed for helium fusion to begin. This involves the combination of three alpha particles to form a carbon nucleus with an evolution of 7.5 mega electron volt. So helium gives beryllium and gamma rays because the beryllium isotope is unstable and breaks apart into two alpha particles with half-life of 6.7 into 10 to the power minus 17 seconds. The second reaction must take place immediately after the first. The sequence is called the triple alpha reaction. The smallest stars do not get hot enough over 10 to the power 7 K to go beyond hydrogen fusion, and helium fusion is far as the star with the sun's mass gets. But in heavier stars, core temperatures can go higher, and fusion reactions that involve carbon then become possible. Some examples are helium carbon, oxygen carbon carbon, magnesium, and carbon carbon, neon plus neon. The heavier the star, the higher the eventual temperature of its core, and larger the nuclei it can be formed. In stars more than about 10 times massive of Sun, the iron isotope is reached. This is nucleus with greatest binding energy per nucleon. Any reaction between iron nucleus and another nucleus will therefore lead to the breakup of the iron nucleus, not to the formation of still heavier one. Then how do nucleoids beyond iron originate? The answer is through the successive capture of neutrons with beta decays when needed for appropriate neutron-proton ratios. The neutrons are liberated in such sequences as hydrogen plus carbon, hydrogen plus carbon, nitrogen plus gamma rays. Nitrogen gives carbon, positron, and neutrino, and helium carbon gives oxygen and neutron. Neutron capture reactions in a stellar interior can build up nuclides as far as bismuth, the largest stable nucleus, but no farther. The density of neutrons is not sufficient for them to be captured in a rapid enough succession for nuclei greater than 2209 before such nuclear decay. However, when a very massive star has reached the end of its fuel supply, its core collapses and a violent explosion follows that appears in the sky as a supernova. However, when the massive star has reached the end of its fuel supply, its core collapses and a violent explosion follows that appears in a sky as a supernova. During the collapse, neutrons are produced in abundance, some by the disintegration of neutron-rich nuclei into alpha particles and neutrons in collisions, and some by the reaction of electron-proton, giving neutron plus neutrino. The huge neutron flux lasts only a matter of seconds, but this is sufficient to produce nuclei with mass numbers up to perhaps 260. A supernova explosion, which occurs once or twice per century in a galaxy of stars like our own Milky Way, flings into space a large part of star's mass, which becomes dispersed in interstellar matter. New stars and their planets, such as our own, that come into being from this matter, thus contain the entire spectrum of nuclides, not just the hydrogen and helium of the early universe. We are all made of stardust. Because triple alpha reaction, because no sufficiently stable nuclides with atomic numbers 5 or 8 exist, there is no simple way in which proton, neutron, and alpha particle can add together in succession to form the nuclei of carbon and elements of still higher atomic number. Eventually, it becomes clear that three alpha particles could react to produce a carbon 12 nucleus in stars whose interiors are sufficiently hot. However, the cross section for the process seemed too small for reaction to be significant. Then in 1953, British astronomer Fred Hoyle realized that resonance associated with triple alpha process would greatly enhance its likelihood. Hoyle's calculation indicated that the resonance would correspond to an excited state of carbon 12 of 7.7 megaelectron volt. Experiments soon showed that the excited state indeed occurred and increased the cross section by a factor of 10 to the power 7, thereby removing the biggest obstacle to understanding the origin of elements. So this was it. See you in the next one.